right. Thank you to anyone who's watching right now. We're going to wait just one more minute to get started because there's a slight delay when we stream to Facebook Live. All right. So thank you so much to everyone who's joined today. We're going to get started. So this event is part of National Drive Electric Week, which is an annual electric vehicle events campaign. Every year, volunteers host lots of electric vehicle events all across the US and even internationally. This year, we took things online because of the pandemic, but we're happy to be here talking to you about EV battery recycling and reuse. Also, National Drive Electric Week is presented nationally by Plug-in America, the Electric Auto Association, and the Sierra Club. And this event is presented locally by Plug-in America. All right, so my name is Kylie Morgan, and I'm the Assistant Program Manager at Plug-in America. I manage National Drive Electric Week and our other April campaign, Drive Electric Earth Day. We're also going to be joined by Bryant from ReCell Center and Zarko from American Manganese. And they're going to do a deep dive into battery recycling. Before we get started, a huge thank you to our sponsor, Nissan Leaf. They're the exclusive automotive sponsor of National Drive Electric Week. And they've been a sponsor since 2012 and have really been a great supporter of our program. So before we get started, I'm going to play a brief message from Nissan Leaf.
To rack up 5 billion miles, you've got to be dependable. The all-electric 2020 Nissan Leaf. J.D. Power's most dependable compact car.
All right. Next, we're going to go right back to our slide deck. Okay, so before we get into battery recycling, I'm going to very briefly talk about battery reuse. So after 8 to 12 years in a vehicle, lithium batteries used in EVs are likely to retain more than 2/3 of their usable energy storage. So generally, when an EV battery uses about 20%, when it degrades to about 20%, and it can only use about 80% of its original capacity, that's when it's time for it to be retired and reused. And depending on their condition, they can deliver an additional 5 to 8 years of service in a secondary application. Also, everything on this slide is from the Union of Concerned Scientists, and so that's my source for this information. So EV batteries can be reused by being refurbished for use as replacement batteries. They can also be used as stationary energy storage. Right now, there are many pilot projects exploring battery reuse and recycling, and I've listed a couple of them here. So at Nissan's European headquarters in France, they do have a system of 12 second life Nissan Leaf batteries, and it helps them manage energy demand and use time of use electricity rates. There's also another example at an arena in Amsterdam, where they're using 148 Nissan Leaf batteries in order to decrease energy costs and provide up to 1 hour of backup power to the arena. So this industry is really just beginning, but there is a lot of research and thought going into how these batteries can best be reused. Automakers are also thinking about designing their batteries so that they're easier to reuse, to get ready to be reused for a secondary application. All right, so next we're going to do a deep dive into battery recycling, and I'm going to pass it off to Bryant from ReCell Center.
Hello, my name is Bryant Polson. I'm the Deputy Director of the ReCell Center, which is a Department of Energy Vehicle Technologies Office program that's located at Argonne National Lab, and we're focusing on the recycling of electric vehicle batteries. To give people a little bit of a background on recycling, we'll start with how are the materials, and mostly focused on the cathode right now, how those cathode materials are made. And you can see the blue line here on this graphic is what the virgin process would be to make a battery from scratch. So you mine the minerals, you refine them, turn them into a cathode product, make a battery, goes into an electric vehicle, and then there's several options at the end of the life or their primary life, and that could be landfill, they could go to second use, or they can go into a recycling loop. And right now there's three distinct recycling loops that are being done and researched for electric vehicle batteries. So the first one, which is the outside green loop, which is a pyrometallurgical process. In this process, the batteries are essentially put into a crucible, burnt, and certain metals are allowed to be are captured in that process, mostly your nickel, your cobalt, your manganese, and your copper. But you end up losing a lot of potential material that's still in the battery, which would be, say, the graphite, some of the organics, as well as the aluminum and lithium in that process. So the metals that come out of the pyro processing then need to be refined, and you can see they re-enter the product stream at the refining step. In the hydrometallurgical process, the batteries are processed and you can get a lot more of the components out, potentially the graphite, some of the electrolyte components, and the foils. But in this case, these materials are dissolved in acid. So you're breaking down the structure of the material, recreating a salt that is then used in cathode production. And then that cathode material, of course, is built into a battery and then goes into a car. The main process that the ReCell team is looking at is what's called the direct recycling. So our processes that we're looking at is we want to capture as much of the process value that was put into these materials the first time through and not break them back down into either salts or metals. And so that's what the small loop is if we can direct recycle material, we can put it directly back into the manufacturing process. And the reason why that this process is important is if you look at the bar chart on the right, dependent upon the commodity price of the elements in your battery, which is what these blue bars are, it may or may not make sense to use these different recycling methods on that. If if you have lithium cobalt oxide in your batteries, the elemental price or the commodity price of cobalt is high, so it does make sense to recover that. But as you go into, say, lithium iron phosphate, the iron is very inexpensive and really not worth recycling. And so what we want to do is look at capturing the price of the cathode material, which is the orange bars here. So that would be the value of the recycled material if we use a direct recycling process. So those are the main processes that industry is looking at and using to address electric vehicle battery recycling. Next slide. So this fits into the Department of Energy Vehicle Technologies office's bigger picture. And so really what they want to do is drive down the cost of lithium-ion batteries to increase the adoption of electric vehicles. And there's three ways that they're doing that, or three programs that they have. The first one is what's called the Next Generation Low Cobalt Battery R&D. So cobalt is one of, as you can see it in the previous slide, is one of the more expensive components in a battery. So if we strip out the cobalt and still maintain the performance of that material, that would lower the cost of lithium-ion batteries. But if we do that, then we're taking out one of the commodities in the recycling stream that would make recycling valuable. So that's, again, why we need to look at that direct recycling loop, because we need to hold on to that process value put into that material. So the second program is the ReCell Center, which is this lithium battery recycling R&D center. And it's a collaboration of 3 national labs and 3 universities. And we're looking at all the different processes that it will take to put together a direct recycling process. So this is really looking at, after a battery pack makes it to a recycler, what are we going to do to make recycling of lithium-ion batteries profitable? And then the last one is what's called the Battery Recycling Prize. And this is an effort that is mostly led by industry to look at how do we sort battery packs, how do we transport them safely, how do we store them, and what are the logistics around making recycling of EV batteries viable. And right now, transportation in the grand recycling scheme of things is about 50% of the cost of the entire process to recycle an electric vehicle battery. So that's why that one is very, very important to look at. Next slide. So direct recycling is kind of a high risk, high reward process that we're looking at. And so, you know, we really want to look at cost-effective, environmentally sound processes to recycle these batteries. And so we're doing this by bringing experts across all different types of recycling areas and taking technologies, both existing and novel, and evaluating them to see, you know, what can we do in the recycling process for electric vehicles. And again, outside of, you know, minimizing cost of electric vehicle batteries for everyone, some of these, you know, resources are not native to the United States. So we want to be able to secure, you know, our position in the battery supply chain around some of these resources that are limited to what we have in the United States. So by doing that, we also are able to increase our national security for these critical minerals that we have. And the DOE goal is to eventually get to $80 per kilowatt hour usable energy in a battery pack. And so if we can recycle material at a lower cost than what it would be to create virgin material, then that will help drive down the cost of electric vehicle batteries. Next slide, please. So we've kind of broken up the ReCell Center into 5 main areas. One is looking at direct cathode recycling. And so the cathode is probably the most expensive and most abundant material in the cell. And so that's the one that we want to focus on first. We have other material recovery. So the more materials we can recover economically, the more revenue streams there will be for a recycler to be able to drive towards a cost neutral at a minimum, but ideally profitable process for recyclers to do. We're also looking at design for sustainability. So some like cell design, can we rejuvenate cells while they're still in the pack? Or as mentioned earlier, can we design a pack or systems that would be easier to disassemble to reduce labor cost for later recycling? Then the next one is our modeling and analysis section. And what we have is a TEA or LCA model called EverBat to look at the cost models and environmental impacts of the processes that we're putting forward, and as well as the Libra model that's looking at the overall supply chain system for electric vehicles. And then we also have several cross-cutting projects that touch base in all of these areas. Okay, next slide, please. So this is roughly what our direct recycling process looks like right now. It's not set in stone. It's something that's constantly changing as we are reviewing the status of projects and the successes of it, and then understanding what we do in one process may affect, you know, processes 2 or 3 steps down the process. So we want to make sure that, you know, what we're doing upstream will be able to work downstream. So typically we'll start at the red circle on the right, and that's our end-of-life batteries. The first process would be to shred those batteries to liberate all the different components in there. Then we would like to do our electrolyte recovery. So that could be our solvents and the salts that are in the battery. And then we could potentially do some cathode, anode, and metal separation. So could we separate the different components for starters and form what is called the black mass potentially at this point, which would be the cathode particles, carbon black, and PVDF. PVDF is what holds the electrodes together. Well, to get that product back to get the cathode back into a battery, you need to remove the carbon black and the PVDF. So we have a process by doing that. It could be thermally or it could be solvent based. And then we take that material, and because it is an end-of-life material, we need to fix the material and get it back into a pristine state. So that's kind of the re-lithiation effort. So we need to put that lost lithium back into the structure to be able to make a new battery out of it. But then also we're looking at upcycling. So, you know, when we saw the data a couple slides ago, you know, we're looking at battery chemistries that could be anywhere from 8 to 10 to, you know, 10 to 15 years old. And that is not what is state of the art in EV batteries going forward. And so we have an effort to look at, well, how do we convert these old chemistries into newer ones, and what can we do to optimize for the performance in that? And then once we have that rejuvenated cathode or upcycled cathode, we can then put it back into battery manufacturing, build a new EV out of it, and hopefully close the loop on that. And so, like I said, we are really looking at both the cost and the performance of each of these steps, as well as the environmental impact, because we are really needing to put these processes together to make that a cost neutral or profitable process for future recyclers. Okay, next slide. So one way we do that, I kind of mentioned it earlier, is the Everbat model. And so this is what we look at is we look at all of the environmental, the costs, the emissions, the energy, the throughput, water consumption, recovery, the revenue, and the waste energy, not only in the recycling process, but in the entire life cycle of the battery materials, so that we can do comparisons of different processes. So, you know, we could look at what the cost to recycle an EV battery through the pyro processing or pyrometallurgical processing and get that material back into a battery. We could do the same for hydrometallurgical processing, as well as direct, and understand the pros and cons of each of those processes, and then use this model to optimize, okay, what are the processes that we need to work on to either reduce the cost, increase the throughput, or potentially work on the environmental footprint of it. And so this is a very big driver for the decisions that we make in the ReCell Center on what projects that we want to fund, because we need to make sure that we're looking at not just the performance, but everything else associated with the recycling process, so that industry will have an interest in picking up these technologies and actually taking them to pilot and full-scale industrial scale. Next slide, please. And so, like I said, this is, you know, not a, you know, a lone Argonne task. This is, you know, 3 national labs as well as universities. And this is the whole list of people that have been working on this project. So I definitely need to thank all of these people for their work in this, and especially this work. It's again out of the Office of Vehicle Technologies, where Sam Gillard is our main sponsor for the program, and then want to thank Stephen Boyd and as well as David Howell at DOE for support in this project. Okay, next slide. And just if anyone is more interested in more details, we do have a nice website, www.recellcenter.org. And invite you to go there. All of our technical reports are there, so you can keep up with what we're doing. And if you have any questions or whatever, feel free to reach out to us at recell@anl.gov. Thank you very much.
All right, thank you so much. That was a great. You really put all that science down into colloquial language we could understand. So thank you so much for that. Okay. So next we're going to welcome Zarko from American Manganese, and he is going to take us through the recycling process that his company deals with.
Thank you, and thank you, Brian, for your presentation. It was really well done. Yeah, like I said, I'm going to introduce American Manganese and our recyclable patented process. Next slide. So we are a publicly traded company, so there's a disclaimer and forward-looking statement, but we can move on to the next slide as well. So I don't think I need to tell everybody here that, this is the beginning of a new era, and the electric vehicle revolution is coming. I saw there was a lot of EV owners registered. And with that, I mean, there is a positive impact to the environment, but, we also have to be cognizant of recycling and how that's done. So next slide, please. Like we said, I mean, the electric vehicles seem to have a promising lifespan, 10, 15 years. And like mentioned at the beginning of the presentation, there's a lot of, secondary use as well that's happening. But eventually, there's going to need to be recycling. And so recycling is a certainty. And, we can't keep mining for the materials. So just going to the next slide to speak on some of the current options. So, I mean, there's not a large volume of electric vehicles right now. They're spent as end-of-life batteries, but from the batteries that are recycled, or the solutions that are out there for recycling, Brian had also mentioned this, is pyrometallurgy. So you're using high heat. There is going to be toxic emissions as well. And like Brian mentioned, there was, focus on really just nickel and cobalt recovery, because that's where the value is. But the recovery of those metals is also really low, maybe around 40–60%. And I love that graph that they have, where you see the loops. The product that's made from this goes all the way upstream. So it needs further refining and needs further processing, finally until it goes into cathode manufacturing. And then into an end-of-life battery, and until into an electric vehicle battery. So, I mean, it's not the ideal process. I mean, the direct approach is something American Manganese is going for as well. But you can see it's ironic if you have this positive contribution as an EV owner to the environment and carbon emissions, and at the end of the life of the battery, even after secondary use, it has to be disposed in some way. So whether it's toxic to, landfilling it or burning the battery, it's not completely positive in the full life cycle of that battery. So next slide, please. So some other processes as well. I mean, you'll see a lot of shredding, and that's kind of where recycling kind of gets clumped in, where, there's the direct recycling, the hydrometallurgy, the pyrometallurgy, but a lot of it is all getting clumped into, some will say, oh, we're recycling, and it's getting mostly shredded down, and kind of the batteries being disposed of, but then that material is also being sent offshore, further refining, and as well as going higher upstream. So really what we want to focus is on direct recycling, really compressing that supply chain and not relying on mined materials. So next slide, please. So at American Manganese and the recyclable process we developed, our focus is on recovering the value from the cathode metals. I think Brian had also mentioned this, on how valuable those cathode metals are. I mean, it's combinations of cobalt, lithium, nickel, manganese, and there's aluminum in there as well. And just actually the other day, not to get political, but the president as well had issued an executive order on critical minerals and securing a domestic supply of them, because a lot of these minerals aren't mined within North America. I mean, the US is 100% dependent on manganese as well. So if we want to continue driving our electric vehicles and producing these batteries, we also have to think about where they come from. Mines are also have a reputation for being, not environmentally friendly. So those are some of the things we have to consider. And with recycling, it's an approach that you're reducing that reliance. You're not sourcing from cobalt from the Democratic Republic of Congo, or you're not reliant on Asia Pacific region for some of these materials and the processing of them, if this can all be directly recycled back to where it's found. So next slide, please. So, and like I mentioned, so there's different components of the lithium-ion battery, but when you're looking at the cathode, and thank you to Argoni for this as well. When you're looking at the cathode, it's your combination of lithium, cobalt, nickel, manganese, depending on the chemistries that you're using. And then on your anode, it's your copper with graphite. And obviously there's always some tweaks and improvements being made to the next generation of lithium-ion batteries. But I think lithium-ion batteries will be here for a long time. And these are some of the chemistries that we're going to be working with, and what we have to focus on being able to recover and reuse again. So our focus and why we're as a company focusing on recovering the cathode materials, because in the next slide I'll show you. Next slide. Yeah, the fully burdened cost of let's say just the lithium-ion battery. So that's considering pack thermal systems, battery pack management systems, anode materials, depreciation, like just your fully burdened cost. The cathode is a huge chunk due to the cost of the material. So like cobalt, nickel, lithium, and that, that's when you're looking at news from Tesla and other companies, and they're talking about that figure, getting the battery cost down from at least to $100 per kilowatt hour to make it competitive with internal combustion engines. Being able to recover some of your cathode material, to myself and our company, we see this as a huge opportunity to save costs in recovering cathode material. And for instance, in the cathode, it's not just end of life materials, but it's in the production of this cathode material. So maybe go on to the next slide, please. It's not like, I guess what we have to think about as EV owners and thinking about where the end of the life of the battery will be, maybe that's 10-15 years away, and then it goes into secondary use, but we have to think about where these batteries are coming from. So when we think about where batteries are coming from, the different components have to be made, and it has to meet those specific quality standards, so you don't have a fire in your EV, or your battery doesn't fail prematurely. So everything needs to be right, from the production of the cathode, the impurities have to be low in the material, that comes on the anode side, the electrolyte as well. And battery manufacturing capacity is increasing. We get some of these numbers from Benchmark Minerals, and the numbers are constantly updating. And you can see how much that battery manufacturing capacity by 2028 relates to in EVs. But in that process of making those batteries, before it's even in an electric vehicle, a lot of that gets scrapped as waste, because for whatever reason, let's say it's trimmings in the material, it's cracking, and there's impurities in the material, it doesn't pass testing. So there's multiple stages where that can fail. It's not simply just mine the material, produce cathode material, and then put that in the battery. I think Tesla did the best job at Battery Day explaining what that looks like, where you mine the material, you make your salt, and then they have a whole bunch of stuff happens, plus a lot of water, and then a whole bunch of other stuff happens, and then you finally get in there. But that whole process and that whole bunch of stuff is a lot of waste generated. And even in the most established manufacturing facilities, you can get up to 10% of their capacity going into waste early on. And then we're seeing now a lot of new battery manufacturing facilities come online we're seeing early on that, 30-40% of that can even go into waste. So you think, in familiar with like woodwork, and you're always going to have some kind of trimmings or shavings that they're going to be going to waste. It's a similar process with battery manufacturing, where it's just not going to meet the standards, or some of it's going to be disposed of. So instead of focusing right now as a company in our business strategy, instead of focusing on the end of life batteries and thinking 10, 15 years out, it's now is the opportunity, and using our process to recover that material. So going further up to where the batteries are made, utilizing that waste and recycling it directly back into the process is the approach we're taking. So next slide, please. So for instance, the cathode manufacturing waste. So when the cathode is being made, like I mentioned, for whatever reason, the material is disposed of, it's not used in the battery. So this is before it's even filled up with an electrolyte. You'll essentially have, aluminum sheets with the mixture of lithium, nickel, manganese, and cobalt adhered to the aluminum foil with the PVDF that Brian had mentioned. So in the bottom left corner, you'll see kind of what that manufacturing waste looks like, the cathode manufacturing waste. And right now, I mean, we're not a commercial plant. We have patented technology, and we're working on optimizing and testing our pilot plant process. So we're looking at getting to commercialization real soon, following our pilot plant testing. But really what we've been doing with the pilot plant testing is testing the scrap material. So we've been sourcing this material from, we've received samples from battery manufacturers. We've gone through the different stages of essentially first, separating that material out with the leaching, precipitating it, and then forming a direct product. So, I mean, it's not the individual salts, but it's going directly back. And the goal is to, seamlessly integrate it back into the remanufacturing process of batteries, not going upstream and then having to be further refined and processed, because we also believe that's an additional cost. So we've tested NCA material, NMC material. We've done LCO and LMO as well in the lab. But in the pilot plant, we've been focusing on NCA and NMC. In our patents, we've achieved up to 100% recovery. And like you see here, we've also been achieving really high purities of material. But one thing I also wanted to clarify, or maybe I can go to the next slide just to show. Yeah, this is another example, maybe a better visual. So for instance, there's an example of the cathode scrap. So that's coming from the manufacturing process, not end-of-life batteries. We've separated that material out. So we have the recycled aluminum foil. And what we're producing, so you don't see a separate nickel salt, separate cobalt salt. What we're producing, and the goal is a direct cathode precursor. So like I mentioned, it's not just the mining and putting it all together and then finally going into a battery. On a microscopic level, I don't want to get too technical here, but these particles all need to look and be distributed in a certain way for the cathode manufacturing process and for battery use. And we're looking to go directly from cathode scrap to producing this precursor material that skips all those additional steps of in the supply chain of producing that material. So like Brian had mentioned, that direct cathode recycling approach. So next slide, please. And then, yeah, this is, so the last slide and this slide were both examples of some material we've done for tier 1 battery manufacturers. They've sent us some of their own samples, and we've done some tests for them. The discussions are ongoing. There's nothing that we've publicly disclosed, but yeah, the discussions are ongoing, and we hope to develop these relationships and get our material validated within their process. Next slide, please. And yes, as I mentioned, our patents, we have 2 patents for the process. you can feel free to search them up as well. You'll see that up to 100%, we've achieved up to 100% recovery of the different cathode materials with testing different chemistries. In the second patent, not to say that we're just focusing on cathode scrap. I think as a business strategy, it's the immediate approach. It's in my mind the low risk approach to enter into the business. Dealing with end of life batteries, the logistics, discharging them, handling them, all comes with risks and expertise. Whereas cathode scrap, you can imagine, it's not charged. It can cross borders. It's not considered like your hazardous waste, but there's value in that. But in the second patent, we have still done tests on shredded materials, which is the black mass of all the different components of a shredded battery mixed in. So you have your electrolytes and you have your anodes and your casings. So we have done work on that recovery of graphite and carbon and treating the fluoride and the electrolyte. But I think just as a business strategy, the pilot plant and focus on commercialization and potential partnerships is on cathode scrap. Next slide, please. Following our pilot plant testing, which we're so far have had really great optimization results, continuing to improve on the design, and using that data for a detailed design and construction of what you see here is a conceptual plan of our first commercial plant, which would be 3 tons of cathode scrap per day. So you can imagine with all the battery manufacturing capacity out there that's expected to increase over the coming years, how much scrap it could possibly be. I think there'll definitely be more than 3 tons per day. But this is our first goal, and that could change over time depending on how partnerships or potential joint development plans pan out. Next slide, please. So when you're looking at the material of cathode scrap, 3 tons per day, what we've estimated the capex being to develop a plant like that would be about 12 million. So relative to a mining operation, just mining lithium or mining cobalt, I'd say the price is fairly low relative to a mining operation. But just looking at the potential recovery of the lithium, the cobalt, the nickel, the manganese in just 3 tons per day, and basing it off of their raw material price. So not even basing it off of the price of the upgraded material that's been past that processing and refining stages, and is essentially a precursor cathode material. I think that is much more of a premium price, but we've here for this example used the raw material price just as a visual to see kind of comparison, and looking at with our process and comparing it to the different methods, we don't use high heat. It's a set of chemical reagents that we're using to leach the different materials, and just looking at the cost of that material, so the consumption of the reagent is used to treat the material, and just looking at that as a dollar per kilogram or just less than about $1 per kilogram of cathode material. And we'll be updating these numbers as we continue to optimize our pilot plant project. Next slide, please. And just a visual on how we look to create a circular economy for manufacturing scrap and eventually end-of-life batteries as well. So the immediate opportunity, you look at the different battery manufacturers and some cathode manufacturers. Like I mentioned, there'll be scrap being produced from there, and if we can source that or co-locate our facility within where the scrap is produced, we can recycle and directly integrate the material back into their process. But let's say for the other percentage of cells that do meet the quality standards and end up going into your Teslas and Nissans and Volkswagens and BMWs, you know, that's going to go through its life cycle, whether that's 10, 15, 20 years, whether that goes into secondary use, but eventually, you know, it'll need to be disassembled, it'll need to be shredded, and the different components need to be separated. And so that's some of the work, like you see here, where, you know, we're working with the U.S. Department of Energy and Critical Materials Institute on a project where there's different national labs and universities working on those logistics. So the collection, the discharging, the disassembly, and as well, we have a memorandum of understanding with Battery Safety Solutions that's as well working on a shredding and discharging technique that's then sending us black mass, which kind of lumps itself into that same pile as like cathode scrap and what we'd be looking to process as well. But the immediate opportunity for us and our focus is on the manufacturing scrap. Next slide, please. So, you know, just to think as EV owners, I mean, we are doing our part in the you know, for the environment, but we also have to be cognizant of where these materials are coming from. You know, I think we've seen with Tesla's Battery Day as well how they're focusing on more of a domestic supply chain, focusing on North American mine minerals, because if you're following around, you know, the nickel and cobalt or coming from the cobalt coming from the DRC, and then that being sent somewhere else for refining, and then finally being sent to somewhere for cathode production, and then finally to North America for to be used into an EV. I mean, adding up all those numbers and the CO2 emissions involved there is you know, detrimental as well. So we have to think about all that and where it's coming from. I mean, even if, you know, lithium is abundant and we have more than enough of it, you know, what are we going to do with the waste regardless, right? Like we need to recycle, and we can't just dispose of it, and we can't burn it. I mean, that's also adding emissions at the end and at the beginning and end of the battery's life. So some thoughts to consider. Next slide, please. And then, yeah, if you have any questions, you know, feel free to reach out, you know, email, Twitter, whatever. We'll get back to you as soon as we can and help explain our process some more.
All right, thank you so much, Zarko. Okay, so before we go to our kind of panel discussion, we're going to have myself and our speakers on video to answer your questions. I just want to provide some resources. So if you're looking to purchase or lease a new or used vehicle, you can compare the different electric vehicles and also find incentives by zip code on plugstar.com. You can also ask any EV question by calling Plug-in America's EV support program. The first question is free, and after that, we ask that you donate to our organization since we are a nonprofit. Also, this event is part of Drive Electric Week, so you can visit driveelectricweek.org to find lots of other EV events, both online and in person. And every April, we also have a similar EV events campaign. So you can visit driveelectricearthday.org closer to April when we'll have lots of EV events going on. Okay, so now I'll ask all the panelists to turn their videos on.
Okay, guys.
All right. So yeah, thank you both for those presentations. I think for me, at least, it highlighted that two things, which is that there's a lot of work being done on battery reuse and recycling. You know, so even though this technology is an early technology, and you know, reusing the batteries is an even earlier technology, you know, everyone is looking for the best way to do that. So maybe for either of you, what are the biggest challenges right now to either reuse or recycling?
So I would say, I mean, for the logistics of collecting batteries, who's in ownership, who actually owns the material afterwards. So if it's passed on to the consumer, And that's really all changing with legislation in different regions. You know, is it the OEM that's going to be involved with the end of life, or is it the consumer that's going to need to get rid of it? So right now, those are the challenges in terms of setting the legislation and what are the requirements for how much it needs to be recycled. Sometimes, you know, it's 50%, but then that could be 50% by weight, and you're not really recovering the full value of the material.
Oh, yeah, you got it.
There you go. I would also say that, you know, everyone has different chemistries in their batteries. And everyone's changing their chemistries in their batteries quite often. And so dealing with all of the different chemistries and different vintages is definitely going to be something that is going to be an issue to deal with. That may make it harder or easier to process those batteries, or change the value of how recyclers or materials suppliers view those batteries as. So there could be an economic driver that will affect that.
Great, thank you. Yeah, and also, Zarko, I think you were talking about how all of these materials come from lots of different places. Are there opportunities for these materials to come from more sustainable sources?
Well, I think one of the big people in the spotlight right now is Elon Musk and Tesla, where, I mean, focusing even just on offering, you know, contracts to sustainable, environmentally friendly nickel miners. I mean, there's ways mining companies can make an initiative, you know, to be more sustainable and have more environmentally positive mining techniques. But in some of these regions where you mine them, I mean, you're dealing with all sorts of, you know, geopolitical risks and whatnot. So I mean, there's a push now with, like I mentioned, the new executive order, where focusing on the domestic supply and focusing, you know, doing it right, you know, in Canada and the US, mining those materials, because then you're also shortening the distance traveled by each of those materials. Yeah.
Great, thank you. Also, a quick reminder to anyone watching, if you have any questions, go ahead and add those to the comments on Facebook Live, and we'll try to get to them. All right. And I'm going to just be checking for questions for a quick second here. Well, I guess another question I've always been curious about is for Brian, how do these batteries come from, like, say, the consumer or the automaker to you guys? Are there any processes right now for collecting those batteries at the end of their life?
I don't believe so on large scale, and that's part of the process, or the problem that recycling is facing these days. Is you know, an electric vehicle will show up at a scrapyard, and you know, it could cost a consumer anywhere between $800 to about $1,200 for the scrapyard to take the car, because essentially what they do is they'll drop out the battery and just have a stack of them in a yard somewhere and not really know what to do with them, and then they'll of course shred up the battery and get what they can out of the value of the car body itself. And so that's why, you know, the Department of Energy really, you know, instituted the recycling prize, is to look at, well, you know, how do we make transportation, or, you know, how do we process these batteries, one, so that you actually have the infrastructure to promote a healthy recycling industry, but, you know, and then also hopefully try and, you know, mitigate risks at, you know, current scrapyards that may have, you know, 10 or 20 EV packs sitting around and just not knowing what to do with them. So that's the effort that's being put in on that topic.
Great. And kind of a similar question, in an ideal world, say, 10 to 15 years from now, what would the ideal kind of recycling and reuse policies look like? And this could be anywhere from how the batteries are collected at the end of their life to, how they're reused.
So I would say I could maybe mention, even not even 10, 15 years, but even now where you have battery manufacturing happening, I mean, at larger scales than we've ever seen before, and a lot of waste being generated. So I mean, ideally to have that waste being directly recycled there on site or somewhere nearby, and then just being reintegrated back with a percentage recycled material, percentage mined, slowly reducing that reliance on mine until you reach this critical mass. But that's an opportunity there for battery manufacturers, and I think maybe Brian can speak on this as well. But on the EV side and end of life, maybe there'll be legislation making OEMs responsible for the disposal and treatment of that, and reusing their own materials.
Yeah, definitely policy is going to play, some kind of effect in establishing the recycling industry. That's really out of our hands in terms of what we do. But what I would say is with the EverBat model, which is the techno-economic and environmental model that we are using, we're looking at, okay, does it make sense to put one main recycling plant, say in the middle of the United States, and then have collection hubs, in different locations, and then doing the cost analysis to say, does that make sense? Or, if we come up with a recycling process that uses a lot of water, you're not going to want to locate that in an arid state because the cost of the water is going to be too high. Or if you have a very energy intensive process, you're going to want to put that process where, energy is cheap. And so as we start to look and develop all of these processes, now we can use, the techno-economic models to kind of put the framework together to say, okay, what is the best, model for, for recycling, collecting and recycling and transporting EV modules.
Great. Yeah, it's a very cool opportunity, I think, to be at the beginning when we can take the chance to do it right and decrease our environmental footprint right from the beginning. Okay, so we do have some questions from the audience. One is, can you speak more about things that battery manufacturers can do to make their products more recyclable?
I guess from our approach and what we've seen with the scrap that we've been handling, I mean, it's more so the kind of what's gluing the active material with all the nickel and manganese and cobalt in there and lithium to the aluminum foil. I mean, it's that binder. I've heard of some approaches where trying to use something else that kind of separates easier. I mean, so far with we've had really good success and recovery and being able to separate all that material. But those are some of the things I've heard. And I guess just maybe focusing on that recovery. I mean, battery manufacturers are doing what they're good at, and it's making the batteries. Any waste is, I mean, it's natural for business to get rid of, but I think it'll be a step back to think about, hey, we can maximize this material, we can reduce our costs by not having to source it from somewhere else. So.
Yeah, and I would say the actual pack design itself could really use some updating with a focus on recycling. Right now, a lot of the packs are welded together, and you really almost have to process the entire pack and shred it up because that's really the only way to do that. But by doing that, you now have to increase the number of steps to pull out all the plastics of the pack itself before you get to the components that you really want to, which is the cell components. And also by doing that, you run the risk of increasing the chances of impurity in the materials that you want to get to. And again, it's going to create another step that you have to purify that material before you get to a product that battery manufacturers would want. And so all of that is adding to cost and environmental footprints for that recycling process. So, you know, if you really wanted to get to the cell components now, it's a very labor intensive process to take the different cases off and you know, sort out the different components. Where if you could design your pack from the start with, you know, quick release tabs or things like that, that would make it much easier to have access to just the components you want. That would really help in the overall recycling process.
Great, thank you. All right. Yeah, these are great. I think this is all like great commentary, and I hope really giving people watching a look into how complicated it is, but also how many opportunities there are, you know, when the different groups collaborate. So.
Mm-hmm.
Okay, and we do have a few other questions. I'm just looking through them now. Let's see. So one question is, are these materials profitable to recycle? And maybe if not, are either of you working on projects to improve that?
So yes, I would say it's very, I mean, even in a smelting operation that's going on now, and maybe just more so focusing on nickel and cobalt recovery, you still see them operating even with lower recovery rates of 40-60%. Yeah, the material is very valuable. I mean, compared to like a mining operation with all the additional steps and what they're producing is just a raw material. Whereas in recycling, if you're not producing just a raw material, I mean, you're, especially with direct recycling, you're almost bypassing all those steps of the additional refining, processing, and finally coming up to a premium material that generally sells higher in the market. You know, it's not an agreed upon price like you'd see like in the London, like in the LME. But yeah, that's definitely just looking at even from our perspective with Recyclico, you know, the reagents we're using, because there's really no high heat, it's more so chemical reagents being used to separate materials, to leach materials and precipitate them out. You know, those are relatively lower cost than what's potentially recoverable from you know, of the cobalt and lithium. All of that combined, it's not, you're not just basing off of one commodity that's going to ruin the feasibility of your project. You know, you have nickel value, cobalt value, all of those bringing your economics up.
Yeah, I would definitely agree with that. And, you know, the more revenue streams that you could have in your recycling process, like recovering the graphite, or, you know, having a more pure aluminum foil stream come out, you know, those are all products that a recycler then can sell to different markets to have it, you know, to have other products made out of it. And so by increasing the number of potential revenue streams, whether it's in the battery field or not, is going to drive that recycling process towards profitability.
Great, thank you so much. Okay, let's see some other questions here. And actually, we are just about out of time. Let's see. And I think, okay, so it looks like we covered most of the questions we got. You know, if you have any other questions, definitely you can email Plug in America, info@pluginamerica.org, and we'll make sure to get those answered. You can also email the EV support program. All right, I think that's it for today. Are there any last comments, Darko or Bryant?
No, thank you for having us.
Yeah, thank you for allowing us to talk about the work that we're doing.
Yeah, thank you so much for joining. I think it was really interesting. I felt like the science was kind of put into terms I could understand, and I feel a lot more informed. So hopefully it's the same of our viewers. All right. Well, everyone have a great weekend, and thank you so much for joining us.
Thanks.
Thanks.
Bye, guys.